My name is Sarah Coffin, and here's my homework 1. As you can see here, the robot's starting in a fresh state in the sim, and we're ready to run the modified brain code. So I'll start that up here. And then if we look at the sim, we can see it moving forward. So my strategy for this homework is 2 parts. The first involved the general locomotion code, which was target heading. So for that, I generated the target heading based on the difference in x and y coordinates between the goal and the robot itself using the robot pose. And then I found the angle differential to use as a turn value and then smooth that value out using a clamp function. This is very similar to the in-class demo that we did. Additionally, this uses the arctangent2 function from the C++ library. The second part of my strategy involves obstacle avoidance, which you might have just noticed from the robot navigating around the fire hydrant. So for the obstacle avoidance, I did a tier-based weighting system with target bias, as I like to call it. And I did this to stay consistent with not using globals outside of the callback, so it handles all of the processing for each call within each call. And it works by each of the LiDAR hits between -pi/2 and pi/2 radians, with 0 being the direct front of the robot. Within 1.5 units of the robot, add weight to either the left or right side to determine which direction the robot turns. I'm just going to move the view so you can see it navigate around this wall a little bit better. And so the left and right weights impact the turn direction value. The left and right weights are integers, and they simply accumulate a numeric value. The idea behind this was to save on processing. So instead of an array or other data structures, you just have a number. So as you can see, it's going around the wall. For these tiers, tier 1, which was between -pi/6 and pi/6 radians, or directly in front of the robot, they received 3 points, so it's higher weighted for each LiDAR hit. And then tier 2, which is between -pi/3 and pi/3 radians outside of the tier 1 zone, receives 2 points. And then tier 3, between -pi/2 and pi/2 outside of tier 2's zone, receives 1 point. So it's higher weighted toward the front of the robot. And the idea is that you care more about the things in front of you and avoiding those as opposed to something more so along the side. And then the stuff along the sides, like here, it's encountering the corner and it's falling more towards the -pi/3 and -pi/2 ends of the tier ranges. And since those are weighted lower, and in fact being tracked at all, means that it can be cautiously turning around the corners. The tangent bias part of this system involves the decision-making process between left and right when it's at more of a stalemate. So there's an additional numeric value that's added to the direction the robot needs to turn to align with the target. And this is added to the weight values. So if it wants to turn more towards the left and is trying to decide between left and right, like when it's in front of the wall, based on the weight values, that additional numeric value can put it over more on one side so that it's, in the end, moving more optimally towards the goal. As you can see here, it nears the goal, and it's a pretty straight shot. And the actual turn direction for when the robot turns is the direction left or right of the lower weight value from the weighted system. And so that was my strategy for homework 1. Thank you for watching, and ta-da! The robot made it to the goal. And now it's stopped. And you can see over here that we won and the robot was destroyed.